Hi, we're ready to go. Okay, let's get going. So today we have the practical on the auto-tuning that I showed you on Monday, and then we also, but before that, we have a couple of presentations. We have Yash Satsangi and Tianyi Li, and Tianyi is coming in. He's a remote student, so he's coming in over Skype. So we're going to start with him. Just before we get going, okay. About the rest of the semester, there's a third mini project still to come. That'll be I'll announce that like next week or maybe the week after, and then you'll have a couple of weeks to do that. But then, of course, there's the final projects, which I know some of you have been asking about. This is definitely time to be thinking about your final projects. So, that we've discussed this before. There's some material on the website about this. The idea is that, I want you to be able to choose a project that is your own choice and something that you can get enthusiastic about, because that's the really important thing, that you do a project that is something, that you have some investment in, because that makes it much easier to stick with it and to do good work. So that's the critical thing, that it should be something you care about. The projects, they're practical projects, so the idea is that you build something and you evaluate it or try and figure out what's working, what isn't, try and diagnose it, try and improve it. And it should be on the topic of music signal processing. But beyond that, it's very much up to you. You're not limited to the platforms that you use, but I recommend that you use one of either processing, PD or MATLAB, the things we're going to use, because anything else can get you tied up in the logistics of just building it. But please do, if you haven't already figured out what topic you want to work on, please do spend some time thinking about that, because obviously I don't want you just trying to do it all in the last week or two. I know it's hard because we're still going through the material, so some of the ideas that might make good projects are still stuff we're going to cover. But obviously you can't wait until we've seen everything to decide. So, if there's the stuff that maybe that we've covered already, that is something that's really stuck out for you, and that's a good idea to link to a project. Or you can look at the classes that we haven't seen yet, but the slides are already on the website from last year, so you can get ideas from there. And then talk to me, send me email, talk to Byung Suk or send him email, and try and get some ideas flowing, just so that you can get moving on this. And it's always a problem, right? How to get people, how to schedule final projects so that stuff gets done. In the past, one thing that's worked well, one thing that's worked is having people give proposal presentations earlier in the semester, so that you've had to have thought of something, so you have to give a talk about it. But just because of the nature of, it's difficult to expect you to have a project proposal together when we haven't been through all the class. I felt like it wasn't a good idea, and plus the schedule's pretty compressed for this class. But I guess I would like to. I'd like each of you to have a concrete idea, some kind of idea. And so maybe if you could each make sure that you've sent me an email or spoken to me or Byung Suk by next week, just so that okay, this is a deadline. I want you to actually think about it and have a concrete idea of what you're going to do. Okay, so I just want there to be some tangible object that we can say, yes, okay, you've thought about it, and this is where we're heading at the moment. Okay. All right. Any questions about that? Okay, let's get going with the presentations then. So first up, we have Tian Yi. Are you there?
Yep.
Okay, great. So you're going to be talking about automatic music genre classification. I have your slides up, so
Okay.
please go ahead.
All right. Hi everyone. I'll be presenting on automatic music genre classification, and let's go to the first slide, overview slide. And so automatic music genre classification can be broken up into two parts: feature extraction and automatic classification. I'll be primarily going over the features and then briefly talking about the classifier and some of the results. For feature feature extraction, we want the features that represent the music information that best discriminate between the different genres. And those are typically split into three categories: features about the timbre, features about the rhythm, features about the melody/harmony. For classification, we want to classify the genre using the features that we got. And some systems are expert systems, which implement a set of rules based on your features, and there are a strict set of rules. So something like the rhythm has to be greater than this, and another feature value has to be less than this to be something else. Obviously, this is hard for genres which are not very well defined. For unsupervised clustering, that's a similarity measure that organizes similar music pieces together. The problem with this is clusters are not labeled, and even if musics are grouped into similar clusters, the clusters may not reflect genres. They could just reflect a similarity based on the features used that spread across many genres. And the last approach is the supervised approach, and this is the one I'll be talking about. And essentially, this is just you train on a set of truth data, then you use that to classify unknown data. And I'll be presenting the approach by Xanatakis and Cook in one of their papers. Okay, next slide. So the timbral texture features are primarily based on the short time Fourier transform, and they're computed for each analysis window, each 23 millisecond analysis window. But the actual features used are the running means and variances over a 1 second textural window. And the reason that a textural window is used is because when we experience sound, it's the result of some pattern over time. So the textural window is designed to capture that long-term nature of the sound texture. Okay, next slide. So now we'll go through each of the timbral texture features that were used. The first feature is the spectral centroid, and essentially it's just a center of mass of the spectrum. It's a weighted mean of the frequencies and using the magnitude as the weights. And I just took an example analysis window, and I computed the spectral centroid, and you can see it's kind of about where the center of mass you would expect it to be. And then the next feature is a spectral roll-off, and this is just a measure of the shape of the spectrum, and it's defined as the frequency in which 85% of the total magnitude is below that frequency. Okay, next slide. And spectral flux is a measure of the harmonic continuity, how much local spectral change there is. So a higher value represents a greater change between two sequential analysis windows. So you can see on the left figure, there's a greater change, so the value is higher. And then the next feature is the time domain zero crossing, and this is just the number of zero crossings in the time domain. This is a measure of the noisiness of the signal, and you can see that for a vocal that has mixed instrumental music, you have significantly more zero crossings going on than just pure music. Okay, next slide. Next timbral texture features are the mel frequency substro coefficients, and these are perceptually motivated features based on the mel frequency substrom. The mel frequency is a frequency that is scaled according to perception, and lower frequencies are more perceptually important than higher frequencies. So it's a linear mapping going from about 0 to 1,000. It's about linear, going from 0 to 1,000 hertz, and then increases logarithmically after that to frequency. And then the last timbral texture feature is the low energy feature, and this is just the percent of analysis windows that have less RMS energy than average RMS energy of the entire textural window. And this represents, so music with silences or speech that have larger periods of silence will have a larger percent of low energy than something like continuous music, for example. Okay, next slide. Now we'll talk about the rhythmic content features. These are the features that represent the rhythm of the music. And essentially what is used is a beat histogram. A beat tracking algorithm tracks the beats and essentially just puts the beats into a beat histogram. And these features basically represent which peaks, or whether the peaks are more pronounced or not, and the overall beat strength. So if you look at the classical music, that has a lot of instruments from the orchestra, there's no real strong beats. And then you get a progressively increasing beat from jazz to rock, and then you get a really strong rhythmic structure in hip hop. Okay, next slide. And the pitch content features are features that are more representative of harmony and melody. And here what's used is a folded pitch histogram and an unfolded pitch histogram. The unfolded pitch histogram is just you take a pitch tracking algorithm, you find the pitches, you convert the frequencies into a MIDI note number, and you plot that onto the histogram. And that represents information on the pitch range. The folded version of the pitch histogram is taking the unfolded version, and then the notes are further mapped into just a single octave. And that represents information on pitch classes and harmonic content. And the features on both the folded and unfolded pitch histograms describe the dominant pitch, the main pitch class, and the tonal interval relations. So if you look at the picture, jazz music has a lot more pitch changes than Irish folk. So you'll see a lot more peaks, essentially, in the jazz music than Irish folk. Next slide. Now I'll talk about the classification methods. So once we have these features, what do we do? So one classification method, and this is probably the simplest one, and it doesn't deal with probability distributions at all, is the k nearest neighbor. And what it is all you do is you just take the k closest training set vectors that are closest to your feature vector. So if you look at the picture, the green is your feature vector, and the blue squares and the red triangles are your training set vectors, and you essentially just pick the k closest ones. So if your k was 1, you would say, okay, it's a red triangle. If k was 5, then you would call that a blue square. The next classification method that's used in the paper was the Gaussian mixture model. And this models the distribution of features for each class. You assume that each class has a probability density function consisting of a mixture of k multidimensional Gaussian distributions. And those distributions, the parameters of those distributions are learned during your training, and it's estimated using an expectation maximization algorithm, which is an iterative algorithm that maximizes the expectation of the likelihood function. And then once you have your PDF of the feature vectors of each class, then if you're given a feature vector of an unknown class, you'll just pick the class that has the highest probability of having that feature vector. And another classifier is actually, I don't have it on here, but it's a simple Gaussian classifier. And the only difference here is instead of the instead of the mixture of k multidimensional Gaussian distributions, you just have one multidimensional Gaussian distribution. And your parameters, instead of being estimated by the expectation maximization algorithm, you just use the training data statistics to get your parameters. Okay, next slide. So from all this, the accuracy of genre classification is essentially the maximum for 10 genres is about 61%. And as you can see, when you get fewer genres, when you go into the subgenres, you actually do better. Okay, next slide. And here's the genre confusion matrix. You can see that 26% of the classical music were misclassified as jazz, and that's due to the strong rhythm in some of the classical tracks. And another interesting thing to note is that rock and blue pretty much did really poorly, and they got misclassified all over the place except for classical. And that might be just due to the fact that those genres are more broad than the others. Okay, next. So this, I just found from the International Symposium Music Information Retrieval conference. Every year they have a genre classification kind of contest, and for 2009 the best performance was 73.23% for 10 music genres. Humans with little to moderate training, they have a cap at about 70%. And obviously, with fewer genres, the accuracy increases, and this doesn't necessarily scale when you increase genres because of the vague definition of each genre. Okay, next slide, and next slide, questions?
So you said that the machine algorithms are outperforming people. Does that mean it's kind of that they're better than people?
Well, they're not better than experts, and the people are not necessarily correct either, and the genres are not well defined. So one music piece could fall into many different genres. And I read in a paper that even experts can disagree. Like, for example, Amazon and AllMusic have hundreds of genres, but then their genres don't really overlap. And even songs from the same song gets put into different genres by Amazon versus AllMusic. So it's kind of relative, I guess.
Definitely raises the question: how do you know if you're confusing rock for pop or for blues or for disco? It's not clear what the distinctions mean.
Right.
So the question is, does that mean that there's nothing, that there's nothing more we can do? This is as far as you can go with this kind of classification, or is there just a problem with defining the problem this way? That maybe we need to come up with a definition of the problem that's more, when you can measure it more accurately. Because if we can't, if the ground truth can't even be established to better than 70% accuracy, it's a difficult task to work on.
Well, when people, I saw that they get actually upper or over 80% accuracy if they discount the genres the misclassifications of genres that are close to each other. So maybe, that seems to me that it could do very well if you have a well-defined set of genres, and it could actually be viable, be relatively accurate, or like once you approach the 90% range. No, I didn't hear it.
If we're saying humans are 70% accurate, how do we know? Because, what do we judge
humans against? Well, the 70% accurate is based on people that listen to a representation of the genres, and then they were given like a 3-second clip. Well, the study showed that listening to a longer clip doesn't help with correctly identifying the genre. But it seems like in that study, they weren't necessarily trained musicians or experts, so to speak.
So what is the accuracy of an expert compared to another expert? That is like... there's some number. I mean, there's some, you could imagine having something where you could hold experts and you could their results, and you could say, okay, well, 90% agree in this one, so what's they is true. But then there's some residual thing where, no, we can't get any consensus on this, and so that there's no way.
Yeah. Well, you could also define your genres so that they're not as like overlapping or easy to misunderstand. Like if you classify classical as jazz, you know for sure that's wrong. Whereas something like rock and then the subgenres of rock and whatever are more difficult to see the lines of.
That was great. Okay, so I'm gonna disconnect from Skype now. Okay.
Okay, great.
Yeah, I have it down.
Alt F5, Alt F8, function F8.
There's some problem with
What's wrong?
the resolution. It should be the
Come on,
same.
Diane. What are you using here? This is
Maybe I'll try the full screen.
maximize. What happens if you unmaximize and then re-maximize again?
Okay.
Just unmaximize. Okay, let me see.
Yeah, just. Maybe full screen. No? Yeah.
How much are we missing? Is that stuff?
No, I don't think we are missing anything.
Okay. All right. You good? You gonna use audio?
Yeah.
Okay.
Hi. So my name is Yash, and My presentation is on bird song synthesis. So this is a small overview of what I am going to present. There's a slide dedicated to each topic. The first one is like why I chose the bird song, or why would be one really interested in analyzing a bird song. The second is a small analysis of bird song, how the structure of a bird song is in frequency domain. Then there's a slide on mechanism of sound production in birds. That is the whole mechanism of sound production, including the syrinx and the bronchia and the oscillators. Then there's a model for bird song synthesis based on the mechanism for sound production, and then there's a small demo based on the model for bird song synthesis. So why bird song? So a good question would be that who would be really probably interested in analyzing a bird song? I mean, who wants to do it? So it's actually a good a very important tool for environmentalists, because it gives a good insight into bird behavior. Then it also gives a good insight into evolution of bird song. Now many scientists connect that evolution of bird song to evolution of human languages, so that becomes an important part for some scientists. And then it's a language for birds, because I mean it's difficult to imagine that birds do communicate among themselves, but the bird song do have a structure, that is they do have a syllable, they do have a phrases, and the whole thing is a song, so they do have a structure among their song. So, and then most important is bird life conservation. So for birds which are already under some dangerous status, then for them it is not possible for the scientist to catch up a bird and ask him to speak at some particular location to attract other birds. That's not possible. So for them it's a good tool to use if a good artificial bird song production can be done. Then it's a natural sound, so it's always interesting to see the different mechanism of natural sound production and the different structures to how natural sounds are. And then another application is to identify the bird species based on the song. This is also another of very important application. Okay, so the main characteristic for bird song is diversity. Of course, it's like, I mean, every bird has a different kind of voice it can produce, and it's quite common in our daily life. Like we hear so many voices from sparrows, pigeons, so that's quite they do have a diverse range. Then they can produce voiced and unvoiced sound. For voice sound, the fundamental frequency usually lies between 100 to 1 kilohertz. Another important thing is they can emphasize the harmonic structure in their speech. That is, they can change the harmonic content based on the filtering properties of their throat, which I don't know whether humans can do or not. Then they can produce pure tonal or whistling sound that does not include any harmonics. So there are many times that you encounter a bird song where there is hardly any harmonic structure, or you can say there is a lot of not non-harmonicity, but there is no harmonics at all. There's just a whistle tone. And another important thing is that humans cannot control the voice pressure in their lungs separately, but some birds can control the voice pressure in their two lungs separately, so they can produce two independent carrier waves. So these are some spectrograms of bird voices. So you can see over here that this is purely a tonal sound. There is hardly any harmonic structure to it. Again, this does have some harmonic structure to it, but this part is again tonal. So how the syllable and phrases are composed is that this would be considered to be a syllable, this part, for this spectrogram. For this spectrogram, this part would be considered to be a syllable, and this would be another syllable, and this whole thing would be a phrase, and when extended for some longer time, then it would turn into a song. Another important thing to notice here is how frequently how good control the birds have over the tones they produce. I mean, you can see how fast the tonal sounds are changing. It's really very fast, and I mean that emphasizes how good control the birds have over their throat, or the oscillator, or the air pressure which they can control, the muscles through which they can control the the production of sound. Now this is a diagram for the mechanism for the bird song production. So yeah, so these are the bronchus. This and this are the bronchus. This is the syrinx. This part, the ringed part, is I think the syrinx, and this is the trachea, and the black dots are the muscles which are attached to the trachea and the bronchus. So syrinx is the main oscillator that is inside the bird. It's like the voice box of bird, and it is surrounded by muscle to tighten and loosen it. So depending on how he tightens or how he loosen it, it produces sounds of different pitches and different modulations. Then also the air pressure, which I talked about. Since they can control it separately, they can produce two independent carriers, and that also determines the pitch and tone of the sound they produce. Then trachea, and yeah, so how you model that is, how you model a syrinx is basically oscillator, which you can frequency or amplitude modulate. And then there is the trachea. Trachea is, since we are again considering it to be two different bronchias which with different controls, so that is why it is modeled as a 3-port junction, which connects two bronchi and one the vocal tract above trachea. And the third part is the beak. So birds don't have lips actually, so beak is the main part which they open to lengthen the tract of the voice they are going to transmit. So and as a model, it acts like a high pass filter, and it may act like a low pass filter for some birds. I don't know. I mean, it might. So this is the model which okay, it's not visible, but yeah, it's a model which I adapted from a paper from Cars and Avengini. Yeah. So as I discussed earlier, these are the bronchus waveguides, and there are two separate bronchus waveguides. This is the 3-port junction, which is the trachea. Which is the the trachea actually, and this is the trachea waveguide actually. And there's a high pass filter over here at the end, and there's a low pass filter over here. So this is what the basic model looks like. And then the paper provides some parameter for the length of the waveguide, so for different birds. So I haven't tried this thing actually. I have just tried a simulation of the syrinx oscillator. So these are the PD pitches which I got from one of the sites, which are based on Hans Michelson's model. And so these two things are actually controlling the frequency modulation and amplitude modulation of oscillator. So this is the main oscillator, and these two are the frequency and amplitude modulation. And these are just attack decay envelopes for each frequency and amplitude modulation of oscillators. So I'll just show a demo in case. Yeah. So he has provided the whole interface for producing the bird song. Yeah. So if I click here, it's like a bird. It's not that natural actually, but it's quite funny. So this is for one of the bird, and yeah. So for wobbler, it is somewhat natural. Yeah. So you do hear this kind of voice sounds when you walk down our university campus actually, and then you can play with these controls to change the voice. So there's more vibration now, and then there's some other sounds like this. This is like the night owl, maybe the frog. This is like a common sparrow actually, but it's not a common. The bird is not a common sparrow. So yeah, these are the main sounds. And then I tried the additive synthesis by taking a bird song file from net and then processing it in Sphere. Then you using Professor's PD patches for homework too. So yeah, this is the PD patch. So this is using the additive synthesis. Yeah, I don't know. I mean, I don't know how natural that sounds, but that's how it is. There's another file. Just a minute. This is the another file. This is the purely tonal sound actually. Looks like that. And then just to yeah, this is the PD patch for our homework, and so I tried providing the N Mozart notes file for it for the bird song, so it sounds as if the bird is singing that song. So I'll just try that. Say I give this as the file. Suppose I give this.
Volume is no.
Yeah. Thank you. Okay, it's. Can I increase the volume from here? Is it? Okay. So it's. Okay, that's the best, maybe. Yeah. That's quite. Yeah. Okay. And yeah, another thing actually I can show is how the spectrogram actually sounds when I do have a minute left, so let's get that please. So yeah, you can see that it is almost a whistle. I mean, the sound is totally tonal. And for a harmonic structure, so for a hawk it is more of a harmonic structure, because I mean for this kind of sound it's harmonic, whereas for other birds, for many other birds, it is mostly just whistles, like for this. This is another thing. Now it's coming full. Yeah, so and then there are some references. That's it. So any questions or?
Are some bird songs that beyond the hearing range of humans, or all of them within?
No, I mean they might produce sound which we can't hear, but most of them do produce sound which we can hear. So I don't know if they can produce something which we cannot hear.
I think their hearing range is not doesn't go very far. Most of them is actually mostly. I think humans have an unusually wide hearing range. It's
Yeah, for the voiced sound that they produce, it's usually between 100 to 1 kilohertz, the fundamental frequency of the sound. So that is quite hearable.
Do you know why the syrinx is able to produce those pure tones? Because it looks a lot like a larynx.
Yeah, right.
But the point about that is that it doesn't generate a sine tone; it generates this pulse. And a pulse
Yeah,
will have
right.
harmonics. I'm just wondering what it is about the syrinx. That, how is it? It's not clear how it generates a pure tone.
I don't know. I don't know how it generates, but what usually happens is this membrane, the tympanic membrane, is the one which vibrates due to the air pressure. So maybe due to that somehow it might be producing that sound. I'm not
It's
sure.
the same. So human whistling is also quite.
Yeah. Human whistling
I'm
can.
not sure how that works either.
Yeah, human whistling can be actually compared to the bird songs, right? And yeah, I think this the clavicle sac, the air is also made to pass through this particular round figure. So maybe that might be contributing to the fact. Okay.
The PD thing that has the interface. What's interesting there is that you've got like 8 parameters which are generating a lot of different bird songs. So that's it's a higher level of description. It's not just
Right.
describing the individual.
Yeah, but I haven't done that. That actually I took from the net.
But it's that's quite an interesting idea.
Yeah,
Actually,
right,
you can have
right.
sort of say, well, there are these whistles, but actually, you can generalize them and just control
Right.
them.
And he actually went on to improve that interface. He actually introduced more parameters, but I took the simpler one.
Does that? Is that? Do people? I don't know. Is it adequate?
Sorry.
Do people feel that those? Because those obviously are not copies of real bird sounds.
Yeah, right.
They're complete synthetic. Do people like them? Do they think they sound like a bird?
Yeah, actually, on the site, what I read was the author's cat actually used to go mad after hearing that sound. So they do. Many animal might confuse it for naturally, and maybe even humans, because you cannot say that what bird it is, and you might think that it is a natural bird. It's a natural sound.
Any other questions? All right, great. Thank you very much. That was very interesting. Okay. Studying a bird song is very interesting. As Yash said, one of the reasons that people do it is because it's seen as a good model for human speech or communication sounds stuff, and but birds are a nice animal model because they're small and they breed quickly, and you can do things. You can mess with their genetics and see what happens. So there's been a lot of results where people find particular genes that are involved in the that are critical for birds to do their bird song behavior, and then the hypothesis is that the same genes which are present in humans are also part of what allows us to do human language. I don't know the details, but that's the kind of results that come out. And so there's a professor in the psychology department here, actually, Sarah Woolley, who works with zebra finches for this kind of stuff, looking at their calls and trying to understand what's going on. So it's actually a very important and active area of research. But it's strange because it is the question that Rediet was asking, which is like, well, do we even hear these sounds the way the birds hear them? I think energetically we do, but clearly we don't interpret them the same way because we're not the same animals. And so there's always this question like, well, if I listen to a bird song and tell you, well, this is a syllable and this is the important part, that's not good enough, right? That's not actually, it doesn't prove that that's what matters to the bird. But you can try out your hypotheses and then see if the birds respond. I think they do this thing where they they do behavioral experiments where they play birds recordings of songs to see if they can figure out that that's the, you know. And so you could imagine doing that with the synthetic set tones as well. To see if you've got, that would be a good way to prove whether you've got enough details in the song that, you know, is satisfying to the animal itself. Okay, we have like 20 minutes. I would like to actually not go another week without doing any practical. So let's have a quick go with this pitch track, this auto tuning thing. So it's all on the website here. So there's a patch for you can download, and then there are a few things you can try. And then what I've suggested here is the basic idea is pretty clear how the auto tuning works. We're using the Sigmund as a pitch tracker to extract the pitch, and then basically we just got this int operator as a, you know, it's taking the integer part. So we convert the pitch into, well, the pitch comes out in MIDI, so an integer is a whole exact semitone. And so we just add 0.5 and take the int part, which is finding the nearest integer. And then we put it through this smooth my low-pass filter, and then take the ratio between the nearest integer and the actual frequency, and then scale all the sinusoids by that so that we tune it to the integer frequency. But there are a few things in here that are not completely obvious. There's something going on here with this Moses part. There's the actual effect of the pitch smoothing, and then there's some other stuff going on where we have, if you look at the actual my low-pass filter, it's got this extra input which takes an output here. So why don't we see if we can just run that and experiment with a few of those things and see what can go on. And we'll do that for like 15 minutes, and then we'll wrap up for 5 minutes at the end. So if you can, probably do it in groups as well, that'd be great. Is that okay? Everyone is able to get going with that? Okay. Right. That's what I like to hear. Yeah.
Does the traditional industry auto tune that makes careers and all that that must be proprietary to someone, right? That's not an open production?
In the mid '90s, in the late '90s. I mean, there's an interesting story about the guy who developed that. He was not really from the industry. He was from, seismic signal processing, things like that. But then he sort of had this idea that he could do it and put the thing together. And so it was like, I forget the details. I'm sure it's on the Wikipedia page. But it was like, it was sort of outsider who came in and made this thing, and then he patented that. But I think there are a couple of competing things.
Right.
But
Interesting. Yeah, I wonder how that works. If it's just like an open tool, or
If they license it for certain.
it was originally a box, right? It was a hardware realization.
right.
Now it's a plugin that you can get for all kinds of software.
Since you sell the plugin, that's it, right? You can't control.
Right, but I don't think it's open source. I think it's
Right.
but the principle's not that obscure.
Right. I mean,
It's all about the details of how you make it be musically satisfying.
Right.
That's the trick.
That's what I want. Oh yeah, it's much worse. Although there's a lot of artifacts there.
Sure, absolutely. So, I'm not sure. It's not clear what you'd want the output of a pitch tracker to be for that kind of signal, right? That it is it is actually generating some kind of output, but I'm not sure what. It's a degenerate case for the pitch tracker. Okay, let's just take a couple of minutes to round up and then see what we've found out. So, anybody have any observations that they want to report? Yeah. So this part here, the Moses 0. So, what does Moses do?
Threshold.
Right. It divides the signal between two different outputs depending on value.
MIDI 0 is A1.
Right. So MIDI 0 is like some very, very low frequency. But the thing is, the signal pitch tracker, when it doesn't throw anything up, it's a large negative number. So this is basically trying to separate the case where the numbers are like there's no pitch versus something that's a real pitch. So if there's a real pitch, it'll send it out here. If there's no pitch, it won't send it out there. That's the main point, is that it simply doesn't. Because these numbers, this kind of value going into this whole system would mess it up. But I also do this thing of taking it from right out and putting it to the third input of this smoother. Did anybody find out what that does? So the idea is we've got a smoothing filter in here so that we don't, when we have steps, we have actual discontinuous steps in pitch from the quantizer, which doesn't sound natural. If you turn it all the way up, it sounds like this very mechanical thing. So we take that step waveform and put it just through a low pass filter just to get a little bit of a smooth transition. But the problem is if you, at the beginning of a piece of voicing, the filter doesn't know, it doesn't have any distinction between whether there's a voice present or not. It's just doing its thing continuously. And so if you start and the filter's at some other frequency, it'll have this long, scoop in, which will be from some arbitrary point. So I have a third input to this low-pass filter, which says if you hit this input, then whatever the next value you get in, you immediately jump to that value. You bypass the smoothing and you just jump straight to that value. And so all it does is what does it do? It takes the state, right? So this is the long-pass, low-pass filter where it remembers the last value and then, takes a weighted average of the current input and the last output. It takes that state and just copies the next input to the state. So the state is like, oh, actually that's where I was already. So that's the way you make it jump quickly. Anything else that anyone did? Sorry, you want me to use the mic? Yeah, I'll use the mic. Any other observations? Okay, let me just show you what I was doing. There's this idea that, when we listen to it, the slide as it stands, it produces a chromatic scale because it quantizes on the semitone level, and so it just goes through every semitone. But I was thinking, what about if we wanted to make it do a limited set of semitones? And so what I do here is I take the integer, which is our best estimate of what the current pitch would be in semitones, and then I break it up into its remainder, and I divide it by 12 to get the octave, and I get the remainder modulo 12, which is the note within the octave. And I put that into select, which basically takes this value, and this value, which is now going to be between 0 and 11, and I break it up into 11 separate outputs here. And then for each of those outputs, I drive a message here, which is now going to be the new value of the semitone. And then I add back up the semitone within the octave and the octave 12 times the thing div 12 to get the new pitch. And so now, and then I can set this so that now this is a major scale. So the first note and then the sharp above it both go to 0, and then we get the first white note, the second white note, and etc. This is our standard major scale. So now if we play the sweep through that, we don't get anything. can see it's nicely quantized here. And the audio keeps dying for me. I'm not sure why. Oh, it's because it doesn't like me switching between headphone and internal speaker. So now it's the major scale, and we could by changing these numbers in here, we could get different scales out, or in fact we could make it not be monotonic anymore. Yeah.
Do you think, does industry Autotune actually ever do what you just did?
Oh, absolutely. Yeah. So if you get a real, because otherwise it's, people can be off by a semitone quite easily.
Yeah.
So in order to make it sound right, you want to do this, but then you have to know which key you're in. But there is if you get an Autotune plugin, it has this thing where it says, okay, which key is it, or do you want me to figure out which key it is and do this?
And then you have an operator switching between them.
Yeah, I guess that would be the easy way to do it, just to edit it. But a more sophisticated thing would be to have something which actually automatically tracks the key, which is not impossible. By listening to the rest of the music, you listen to the accompaniment, and decide, okay, I'm obviously in C major here, so then you choose those notes. It's all a question of convenience versus when it makes errors. Okay, any other questions? All right, so see you on Monday. But remember, I'm looking for an email or something from each of you by next week to tell me where you're going with your project. Great.